So in looking at this, as time continues, life expectancy, increases and increases and increases, and bam. Actually, there's a little bit of a dip for, countries like the United States towards the end here. Ouch. Don't know if that, don't know exactly what that reflects. I know that there was, part of that was there's a lot more death from suicide and the methamphetamines, no, let's see, the prescription drugs has become a big problem, that people get addicted to that and overdose. So in any case, does it make sense that the increase of time causes people to live longer? Remember, we dealt with correlation before the break, and we can certainly see that as time increases, life expectancy increases, but is it a causal relationship? Does one cause the other? Or is there something else that's a cause of increasing longevity as the years go by? What would you think?
I would think it's more from medical advancements.
Yeah, it's probably better food, medical advances, other advances in technology, etc. So yeah, there's probably a lot of things that go into our increased longevity, but it's not just the mere passage of time. So the mere passage of time is, or time in this would be, correlated, but not causally so. And in the next part of class here today, we're going to look at a causal relationship. But let's look at a fun one for right now. And for that, I want to go over to here, this other data set, this other link that I shared with you. And when you open that up, there's a little icon, a little drop-down menu that you can click up here. And I want us to click Open. So from that little menu up top, click Open. And if you scroll down, we're going to do something kind of fun. And it's, let me just shut this and I'll go back and do it. So up here, it says Untitled Document. Next to that, there's a little downward arrow. Click that, then click Open. And then it gives you a bunch of data sets you can open. And Brittany, your shirt today is perfect, right? I think it says Cedar Point. Is that right?
Yep.
Awesome.
I'm going into resort and attraction management after this.
All right, perfect. Well, you should know a little bit more about roller coasters then. And so just for you, we're going to dig into roller coasters. Now, this opened up two things. I only want one of them. This is a great program. It's wonderful. Now, one of the cool things you can do is you can just click anywhere, and it'll take you to the data point that you clicked on. Now, I happen to click on a coaster called Georgia Score. It's at Six Flags. Top speed of 54 miles an hour, max height of 107 feet, etc. All kinds of information about this. But let me ask you something. What's the most fun thing in a roller coaster? Anyone? You got anyone out there in Zoom land got an opinion on this?
A lot of people like
Airtime is good. I think most people would agree it's going fast, right? I mean, that's certainly one of the fun things about going. Is just going really, really fast. So, and as far as really, really fast, nothing beats Top Fuel Dragster. Yeah, it's quite a rush when you get going fast. For those of you who I wasn't sharing my screen with, well, just let me recap how to get to this data set. So you open up the link, click here, and then open, and then it'll pull up a menu, and you want to scroll down to the bottom one, which would be roller coasters. It should give you this data set. Now, what we want to do is we want to try and investigate top speed. So let's do that. I'm going to move these around a little bit. And if we look at top speed, it's right here in our data set. Let's drag that to the y-axis of our data. And woo, that's kind of cool. It kind of organized itself, right? Into a nice sort of sideways histogram, dot plot. So once again, you just click on this column of data and drag it to the y-axis. And it should give you what you're looking for. Now, the big question is, if you're building a roller coaster, what do you want to do in the design phase to create that real big push, that top speed? Well, there's a lot of possibilities, things that can explain what's going on, that explain this variability. Now, one of them could be the design, and if you click and grab design, drag it over to the x-axis, it gives you something which looks mildly interesting. You can see that there's 6 or 7 different types of coasters. I don't know what the fourth dimension is. There's flying, inverted, pipeline, sit down, stand up, suspended, and wing. But that doesn't seem to be really doing a good job of explaining the variability in the response that is in the y variable. So let's look at something else, like maybe duration, how long the ride lasts. And if you grab that and just drag it over to the x-axis, you should get something like this. And that's a scatter plot. And let me ask you to think back to before the break. I know that that was, a long 12 days ago. But does there seem like much of a correlation between these two variables, between how long it lasts in seconds and how fast you go? Not a great one, right? I mean, it's okay, but not really that great. So what else might better explain that? Well, you could try things like the length, but I'm thinking we might be better off with the max height. Let's try that one. Does that do a better job of explaining the variability in the top speed of these roller coasters? I'm thinking so. It looks pretty good to me. Now, what we eventually want to do in this section, section 10.2, is kind of quantify that relationship. So let me start by reminding you of something here. And let's see. Gotta make this a little bit bigger here. View 125. There we go. And so section 10.2 recall that R was our linear correlation coefficient. And it'd be nice if I got that in focus. And what was the value of the R could take on? R could take on anything between what and what? Do you remember? R was between -1 and 1. Now, R equals 1 was a perfect linear correlation, perfect positive correlation. Perfect positive correlation. This is a perfect negative correlation. And then everything in between, various degrees of positive and negative correlations. All right, a couple people getting that in the chat. Awesome. Well, everyone got that down? All right, let's look back at this and let's try another one. We did max height. How about if we do the drop? Instead of max height, we'll do the drop. And try and keep an eye on this and decide which one you like better. So let's put in the drop here. Oh, drop's not too bad either, is it? It's pretty good. Just for giggles, let's compare it to the length. You know, how many thousands of feet this is. Actually, I screwed up. What did I do? Let's just get rid of that. What's that? Oh, is it? Top right, undo. There we go. All right, so let me try that again. Length. Does length do a good job of explaining things? No, length is pretty bad. I mean, we don't even have to be quantitative to see that. But as far as which one's better between drop and max height, drop looks pretty good, and so does max height. So we need something a little bit more objective to start measuring these and decide, well which one do we really want if we're going to pick one. So here's where some other wonderful magic comes into play here. And that is, if you click on the right-hand side of this graph, midway down on the right-hand side, there's a little icon for a ruler. If you click that, you can have it overlay the least squares regression line. So let's click that, and bam! It puts a little line here for you. Now I'm going to expand this a little bit if I can. Just grab the right-hand corner. And wow, it tells me this equation. It tells me my top speed is 0.193 miles an hour times the max height plus 33. And it says r squared is 0.79. Now we've dealt with r, but now we've got this r squared. So let me write down for you what r squared is. And if you're thinking, well, we got r and r squared, I mean, these seem kind of close. They are. There's no doubt that they are close. R squared is the coefficient of determination. Now I'm going to give you a very user-friendly definition of what r squared represents. R squared represents the percentage of variability in y that is explained by knowing the value of x. Star that one. Know that one. This kind of stuff often ends up on an exam and or the final. Is understanding what r squared tells you. The nice thing about understanding what r squared tells you is that you can now judge different models for your y variable. Now what do I mean by that? Well, let's see if we can't take a look here. Let's see, can I get rid of that? That keeps on letting me go back. Eventually it should give me what I want. No, it doesn't. All right, maybe I can just close this one out and go to open. Yes. There. So if I go back to this data set and just put max height, no, not max height, top speed here. This is just showing you the y value, the y variable, and there's a lot of variability in this y variable, right? I mean, at the top end, and Brittany, here's your chance to shine. What's the fastest roller coaster in the world? Is it? I thought it was Top Fuel Dragster.
There's actually one in between that too. It's King to Cop.
Really? All right. Well, the fastest one in this, you ruined it. So I was looking for you to say Top Thrill Dragster, but that was pretty fast. 120 miles per hour. And on the slow side, boy, man, I don't want to put my kids on this one. They'd be pretty bored. 23 miles an hour for bobsleds? Okay, yeehaw. But in any case, there's a lot of variability in the y variable. And that's all we're doing is just looking at the y variable. Now, a lot of that variability can be explained if you know the height, the maximum height of that first hill. Boy, that does a pretty good job. How much of that variability are you explaining? 79% of it. There it is, 0.79. So, what's better to use in our model? This one or the vertical drop? Well, let's just put vertical drop in here and see what happens. Take a look at the value of r squared now. What's r squared now? 0.838. Does anyone know how I would get the value of r if I know the value of r squared? Woo, bravo. Take the square root of it. Yeah, that's all you have to do. So if we take the square root of 0.838, let's see what we get. So let's do that. Square root of 0.838. And you get a linear correlation coefficient of about 0.915. That's really good. And that kind of matches what you see when you look at the data, right? When you look at the data, it looks pretty close to a straight line. Is it perfect? No. No. And Aisha got that one, and so did Sonia too. Thank you. All right. Let me go back to our data set. Let's understand this a little more. They actually gave you something that we can get an equation from. Let me remind you about some equations before we actually look at that. The equation of a line, zoom out a little bit. So the equation of a line is generally written like this. Y equals mx plus b. What's the m? What's the b? Does anyone remember? I know this is not an algebra class, but I know there's at least one of you. M is the slope. Yeah, yeah. Well done. Bonus points. So this is your slope. This is your y-intercept. Perfect. So let's remind ourselves what the slope and the y-intercept reflect. So I've got a little graph here, y equals mx plus b. And right now I'm tinkering with the slope. As I increase the slope, the line gets steeper and steeper and steeper, right? Of course, I could have a negative slope, and a negative slope would mean that as you move from left to right, the line is moving towards negative infinity or moving in the negative y direction. But there's a special case in between. Now let's see if we can't get to that special case. I'm getting closer and closer to m equals 0. What's going to happen at m equals 0? What's my line going to look like? Going to look like a horizontal line. Yeah, a couple of you getting that. Thank you both. So let's put in m equals 0 here. And bam, there's your horizontal line. So a horizontal line is kind of special in as much as if you're trying to make a prediction of y, knowing the value of x, usually it makes a difference, you know, what your value of x is. Like here, if x is 5, if x is 5, then y is 5 plus 3.5 would be 8.8, or 8.5. So there you go. There's your point, 5 and 8.5. But when m equals 0, it doesn't matter what the value of x is. Your guess for y is still always going to be the same. So that's why we single out that value as being special. We want to know, is the slope 0 or something different than 0? Because if it's something different than 0, then knowing the value of x helps you understand something about the value of y. So now let's look at our output from the roller coaster data set. And here it is. It tells us that our top speed is 0.205 miles per hour times the drop plus 34 mph. All right, so let me write that down. So it's going to be your top speed equals 0.205 times the drop plus 34. And let me give you an interpretation for that as well. In fact, maybe you can help me out with the interpretation. All right. What's the slope in this one? Yep, there's your slope. So what this is saying is that for every extra foot of height that you build for this roller coaster, you're going to get an extra 0.205 miles per hour. So for each extra increase in x, you're getting 0.205 miles per hour more out of your speed. And in fact, just by building this, you're starting out at 34 miles an hour, which begs the question of what they do wrong to get that one that we looked at earlier with a top speed of 22 miles an hour. All right, but understand what this is. This is just a mechanical process to fit a line to your data. It's not interested in trying to give you a nice, easy interpretation. It's just a mechanical process to say, all right, this line fits your data best in some sense that I'll discuss in a little bit. Okay. Let's continue. And I like to throw in a little review, especially as we're getting towards the end of the semester. So let me review a little bit in this way. Sample, population, mean, standard deviation, proportion, correlation, and regression. So let's remind ourselves about some of these symbols. Let's start out with the sample mean. What do we use to represent the sample mean? X bar. Excellent. How about the population mean? Mu. Standard deviation? S and sigma. Nice. Proportion. P hat. Right? And P. Good. Well done. P hat and P. Now this is a new one. A newer one. You remember what the correlation was? One more time. R. That was a correlation. And how about the population correlation? No, not R squared. Ah, well done. A couple of you got that. Rho. Well done. And rho looks a lot like a P. I won't kid you, and I can't deny it. It looks a lot like a P. All right, so that brings us to our last one. We're going to try and come up with a regression line or regression equation. And I'm going to give you a couple choices here. So So let me open up your handout. And I'm giving you two choices. It says, what's the difference between the following two regression equations? And I'll tell you, the difference is that one of them is the sample statistic, one of them is the population parameter. But which one's which? Which one do you want to write down? Where? Should we answer A or B here? Let me see if I can't improve the view a little bit so we get everything there. All right. A little bit smaller, but hopefully still works for you. So what do you think? Which one should I answer where? Try and write it down for yourself first. So my people here, you can answer 1 or 2. My people online can answer A or B. But just hold up a finger. Which one do you think is which? Should we answer the first equation for population, the second equation for sample? That would be A, or the first one. Or B is the first equation for sample, the second equation for population. So, all right. All right. Oh, okay, good. It was behind your water bottle. All right, let's see how we're doing on the chat. All right. All right. Yeah, so the trend that I wanted you to see, and it looks like a lot of you spotted it, was that all your Greek letters are associated with population parameters, always. And your hypothesis tests are always going to be the same way. They're always going to have population parameters in it. You should never be writing any of these values or symbols in with your hypothesis test. Now, y hat is your observed, or excuse me, predicted value. So based on the equation that you come up with, you can make a predicted value. That's your y hat. And along with that, y is going to be your observed value. These are the population parameters. We're hoping to find that our value b1, that is the slope of our line, is something other than 0. Because if this was y equals 0, x plus something, it'd be a really boring line. It'd be a horizontal line. I mean, knowing the value of x tells you nothing about the value of y. That would be boring. So you're hoping to get rid of the possibility that beta 1 is 0. And we'll find out. Now, y is your observed value. And what we're trying to do with the least squares regression line is make the difference between our observed value and our predicted value as small as possible. Now that value is called the residual. So the residual, which I can also call E, is y minus y hat. And it's basically your error. If you do this calculation for every value in your data set, then what the least squared regression line is trying to do is trying to make the sum of the square of these values as small as possible. And there's a mechanical process to do that. It's something we don't have to really worry about because technology takes care of it for us. So let's take a look at some more of the problems that you're going to see in your homework. What is the residual? In what sense is the regression line the straight line that best fits points in the scatter plot? Well, what's the residual? The residual is just the difference between y and y hat. So let's see, residual is a point that has a strong effect on the regression equation. No, that's not it. What do you think about B? Residual is the amount that one variable changes when the other variable changes by exactly 1 unit. No. Does anyone know what they're describing there? That'd be the slope. You change the input by 1, then how much does it change the output? That would be the slope. How about let's look at D. A residual is a value that is determined exactly without any error. No. So that must mean this one looks pretty good. Residual is a value of y minus y hat, which is the difference between an observed value of y and a predicted value of y. Perfect. That's what a residual is. Basically, it's your error. And you want to make the error as small as you can with a good model. Let's stick with this idea of a slope and an intercept and look at some more examples. Trying to remember, I think it might be example B here. Different hotels in a certain area are randomly selected and their ratings and prices were obtained online. Using technology, with X representing the ratings and Y representing the price, we find that the regression has a slope of 130 and a y-intercept of negative 365. Complete parts A and B below. So I think we're only going to do part A. But let me write down the important stuff for us here. And that is that the regression equation has a slope of 130, and a y-intercept of negative 365. So, let's see. So example B. M is 130. And B, it looks like negative 365 to me. If I wanted to emphasize that I had a negative number, I'd probably put it in parentheses just to try and be a little bit polite. Like, okay, I didn't just put the dash there or something like that. In any case, let's see if we can't come up with the equation here. Why don't you see if you can't come up with the equation first? Recalling that our equations are going to be in the form y equals mx plus b, then let's see. It's going to be a 130x plus negative 365. Now, if you wanted to write it as 130x minus 365, you'd certainly make me happy. But there's actually a little bit more to it in our answer than just this. So let's look back at our possibilities and see what's going on. So they're asking for the regression equation. Now there's two of these I can eliminate right off the bat. Which two can I eliminate without even hesitating? Go ahead. A and D. Good. Can someone tell me why? Why does she say A and D? Why can we eliminate A and D from consideration? Take a look at the left-hand side of the equation there. What is? Well done. It's not y hat. Good. So let's get rid of A and D. So let's see. Bye-bye, bye-bye. And now if you were to guess, you'd at least have a 50-50 chance. So if you're taking one of those tests where they penalize you for wrong guesses, give you 0 points for no guess, then at this point, statistically, it's in your best interest to take a guess. Because on average, you'll make more points than you lose. Now, the other part of this is decide between B and C. Did I discuss X hat? Yeah, I don't think so either, because there is no X hat. So we can eliminate that one. And basically, it comes down to this one. That's your equation. Y equals something plus something times X. Now keep in mind that this is backwards from the way I write it. I don't know. Maybe it's because the author spent too many years teaching statistics and hasn't taught an algebra class in a while. But For me, it's always this, y equals mx plus b. Or in our case, y hat. Now, if you're inputting it into my stat lab, you have to put it in a different order. Negative 365 plus 130 times x. So, yay. That would be your answer. So each time you increase the number of stars in your hotel, what happens to the price? Does it go up or down? Remember, X was the rating of your hotel, and Y was the price of your hotel. So I'm assuming they're talking about the price for one night stay. If I increase the number of stars in my rating, what happens to the price? What does it go up by? By how much? Ooh, no. Sorry. But I appreciate the effort, though. Yeah, it goes up by $130, right? So every time you add one more star to your hotel, the price of it goes up by $130. Now, is there a good interpretation for the negative 365? No. I mean, basically what this is saying is, boy, you better at least have 3 stars, otherwise you're going to be paying people to stay at your hotel, right? Because a 1-star hotel would owe you $235 is the way I'm reading this equation. And that's kind of a tongue-in-cheek way of saying that these equations only work so well. They work good for the data that you've got, but sometimes when you try and stray too far beyond the data, make predictions way far out in the future or something like that, that they don't always work. And you're not always going to have a nice interpretation for this. We will see a problem where there is a nice interpretation, but right now, there's not a good interpretation for this. It's just a mechanical process to fit a line to that data. That's all it is. I mean, when this program CodeApp does its work here, it's not going, oh, well, what would be a pretty line? What would give you a nice interpretation? No, it's trying to minimize the sum of the squares, squared errors. So the least squared regression. Okay, let's keep going. I think this might be example G that we're going to do next. Yes. So sticking with the same kind of theme where we're going to try and interpret these regression equations. And by the way, interpreting these regression equations in words is a great question. Because at the end of the day, you can do all the wonderful statistics in the world, but unless you can communicate your results, what good is it, right? I mean, somebody has to know and understand what you say. So let S be the sales of frozen food bowls in millions in the year that is T years since 2002. Now, let me see here. A reasonable model of the frozen food bowl sales is S equals 32T plus 312. So, all right, let's write that down. Call this example G. I apologize that we're not going in a nice alphabetical order. I looked at it and said, you know, I just don't have the energy to change these up, although I liked the order here better. Example G. S equals 32T plus 312. And they're going to ask us a couple questions. Let's refer back. What's the slope? Somebody just tell me what the slope is. 32. All right. A couple people on that. Good deal. 32. All right. So 32. That's our slope. Let's keep going. It says, what does the slope mean in this situation? So the slope is 32. The sales of frozen food bowls are decreasing by blank million per year. The sales of frozen food bowls are increasing by blank millions per year. So, what do you think? What's happening to the sales of frozen soup or frozen food bowls per year? Increasing by how much? You keep on going to the y-intercept. It's increasing by the slope. So each additional year, every extra value of t, you're adding 32 more onto this number. So you're adding 32 more million bowls of frozen food to this total. So for each increase of 1 year, the number of frozen food bowls sold increases by 32, and that's in units of millions. Nice. Under what condition would it be decreasing by 32 million? Yeah, well done. If the slope was negative, then it'd be decreasing by 32 million. Okay. Nice. All right. Let's get our hands dirty with some data. And let me look at this. I might have the actual number wrong. Let's see, example D. F. Yeah. I think it might say example D on our website, or it might say example E, I'm not sure. I think it might say example E. Anyways, let's go to the website. Yeah, it says example E. It's really D. And if you copy that data, I'm hoping that it'll paste into StatDisk nice and easily. So let me do that there. Nope. Oh, not again. Oh boy, this is such a bummer. Let's see. Actually, you know what? I'm going to put that one here. Delete there. Now I've got the same data set. I'm just changing the order of 1 point to make it easy on me. But let me see if I can't paste this one in now. Is it pasting in for you okay? It didn't paste for me, which I find irritating. Let me put that data set in the chat for those of you online. How about those people here? Does the data set paste in okay? No? That's so frustrating. All right. Let me redo that. Edit. Okay. Try it again. I think that one should go. If you're logged on, you might have to hit the refresh button to make sure you get the most recently updated piece of data. Okay. Do you guys get the data in? Okay, good. So if you're taking a guess as to where you're going to go to help analyze it, then a good place to start would be the analysis menu. And if you scroll down, what do you see that looks interesting and promising? correlation and regression. In fact, they're essentially the same test. You're using the same test now that you did last week or 2 weeks ago when we were testing correlation. The difference is we have a different interpretation now, or an additional interpretation than we did last week. So we'll select column 1 is going to be your x's, column 2 is going to be your y's, and just click evaluate. Doesn't get much easier than that. Now, amongst the things that interest us here is the equation. And the output here is kind of basic. They tell you, all right, we're going to write it in the form of b0 plus b1x. Okay, great. Now, they didn't even subscript it. They just put b0 and b1. All right, whatever. I still like StatDisk. In any case, see if you can't write the regression equation, given that they told you what b0 and b1 are right here. And round your answer off to the nearest, I don't know, third decimal place if you want. All right. For those of you on the Zoom, please put the answer in the chat. For those of you here, I'm going to walk around. And what I want to see is the equation. I'm just being picky now because I don't want to do something later. Mostly on homework. Not sure. Okay. Hopefully you don't round it off so much. It's okay. I'm glad you remember the hat.
A hat?
Yeah.
That's what we were questioning, so there's a hat.
Yeah. Little chapeau.
So how do I know when I didn't know what the data was about? I guess is what I'm confused.
How do you know what?
That it was by hat, not just by.
Oh, because this is the output from your regression analysis. So this is fitting your data with an equation. So it's going to be the predicted value. It's not going to be necessarily the actual value.
Okay. Thank you.
Everyone's getting their hats on now. That's good. All right. Good. I don't know. I think there's a couple people out there watching their Pokemon videos. I didn't get equations from everybody here. All right, let's take a look here. Okay. Oh, nice, nice. Now Mariah wrote it kind of like the book does. She wrote it this way. Of course, all of you on the chat, hopefully in your papers you wrote a y hat. Personally, I like writing it like this because that's y equals mx plus b that I've been teaching for, I don't know, since 19 mumble mumble. So now, what we're interested in knowing is whether or not this is a significant regression. So the hypothesis test that we're going to do is this. We're going to test this claim, H naught, such that beta 1 is equal to 0 and beta 1 is not equal to 0. And what does that mean? Well, if this is true, it means we don't have a significant regression. So, not a significant regression. What about if this is false, if you reject that? And this means you have a significant regression. Now, if you don't have a significant regression, then what you would do to make predictions, well, if y hat equals beta 1 x plus beta 0, if this is 0, then it's just y equals beta 0. It's just y equals a constant. That's all it is if this is 0, because 0 times x is still 0. So it just gives you y equals some number. Basically, you're going to use the mean for y hat equals y bar. That's going to be your model in the case where you don't have a significant regression. If you do have a significant regression, use y hat equals b1x plus b0. So you're going to use one of these two models based on whether or not you reject h naught or fail to reject h naught. Now, in our particular case here, our typical values for alpha are alpha is 0.05 or alpha is 0.01. In this case, let's take a look. Let's take a look at our regression. Take a look at the regression output. What was our p-value? Right there. P-value is 0.00163. Does that mean we reject h naught or fail to reject h naught? Say again? Got a couple of rejects. Let's see in the chat. And Michael's there. Sonia's there. All right, anyone else want to weigh in? Yeah, there we go, a couple more. David, Aisha, thank you. Yeah, you're going to reject. Your p-value is less than alpha. So therefore, reject h naught. That means you can use your regression equation to make predictions. You're not just going to use the mean. So if I wanted to make a prediction for when x equals 3, and whatever this data set is, I put in a 3, multiply it by 0.582, and then add 2.188. Just do it on your calculator. All right, it's real easy. Let's take a look at our output, though. Take a look at our regression a little bit more. Click scatter plot. Does that look like our line is doing a good job? What do you think? Is our line doing a pretty good job of explaining all the ups and downs and why? It's not bad. But there's actually something that we can do or look at that quantifies that rather than just the eyeball test. And that is your value of r squared. So let's see. Let's take a look at your value of r squared. So go back to results. What's your value of r squared? Does anyone see it? .686. Now, if you want to know where that comes from, remember I said that this value of r squared reflects the proportion of variability in y that's explained by knowing x. You can look at these two totals. You can look at your explained variation. Let me just type that into my calculator. 32.439 divided by the total variation, 47.269. And let's take a look at what happens when I press the enter key. So this is the variability I can explain. That's the total variability. How am I doing? I'm explaining about 68.6% of that variability. Not bad, but not great. And if you look at the data set, you can kind of see why. So, yeah, there's one point way up here that's kind of skewing this line a little higher than it would be otherwise. It's pulling that one up, right? So it's missing a lot of this data in order to be a little bit closer to this one here. You can see that if you look at the residual plots. The residual plots are going to be the predicted value minus the actual value. No, the other way around. Actual value minus predicted value. So that distance there. Let's look at the residual plots. So you see we got a big residual here. And am I calculating my residual backwards? This would be the observed minus the expected. Okay, yeah, so it would be positive. So look here. You're off by about 3 here. The rest of your data, you're not off too bad. I mean, this one's not so good. But boy, this one is kind of a pain here, isn't it? Let's look back at our data. And if you picked up the data set from what I sent you, let's just delete that one observation, which I think is right here at about 13 and 13. Let's take a look at our scatter plot. Yeah, 13 and 13. Boy, if we didn't have that 1 in the data, let's see what happens to our regression. What do you think is going to happen to the value of r squared when I rerun this? Is it going to go up, down, or stay the same? Value of r squared is the percentage of explained variability. Do you think the line is going to fit better without that point, or about the same, or worse? Should probably explain it better. So take a look at the value of r squared now. About 0.93. That's really good. Let's take a look at the scatter plot, see if we did a lot better. Yeah, scatter plot's a lot better, right? You're much closer to all your data because you're not being pulled up by that one really strange value. If you look at your residual plot, things look scattered. That's okay. You don't want a pattern in your data, in your residuals. Because if there was a pattern, that means there's probably another term in the model that we could be taking advantage of, and we're not. So it's okay not to have a pattern in your residuals. But your scatter plot looks great. And it's reflected in the value of r squared, the coefficient of determination. You're explaining a lot more of the variability now than you were just a minute ago. Okay, let me pause for a second. Questions on that much? I know we've gone through a lot. Are you okay that the coefficient of determination is explaining the proportion of explained variability? If you take a look at the ratio of these two, explained variation divided by total variation, you're going to get your r squared. That's where it's coming from. And you're doing really good here. You can see it from the scatter plot. Our data is very close to the line. Going back to the results here, suppose I had the value of r squared. So r squared is 0.9288. R squared is 0.9288. What if I wanted the value of r? How would I find the value of r? Take the square root of that number. Let's see what we get. Let's see, I don't want to wait for that thing to open up. So, square root of 0.9288, 0.9637. That's another good test question. I can give you an r squared and ask you for the r. 0.93, which is going to be 9637. That's pretty close to what magic number? That's close to 1, which would be a perfect linear correlation. That's very close to 1. That's outstanding. In what case would I have to choose the negative? Because you remember, there's 2 square roots of this. There's the positive root and there's a negative root. At one point, would I want to choose a negative value here as opposed to the positive value? Ooh. What? Let's see. If it was a negative correlation. So if this scatter plot was sloping down as opposed to sloping up, that's when I would choose the negative value for R as opposed to the positive value. That's another good test question, just FYI. Kind of a simple one. I give you the value of R squared and ask you to calculate the value of R, but I'll also give you the scatter plot. And you have to look and see, do I want the negative root or the positive root? 2 points for that answer, one for getting the square root, the other one for getting the positive or negative sign correct. Nice. Nice. Let's keep going. Now, just a quick FYI. Sometimes the data that you get from my stat lab will have commas in it. And what is it? StatDist does not like commas. It will bark at you if you try and use the data set that have commas. So one way that I've gone around this to clean this up is I'll take my data and I'll paste it into Microsoft Word. And Microsoft Word has a little thing here. In fact, let me just change a couple here. So I'll put a comma in here, and a comma in here, and a comma in here. So if you do find a comma and replace it with nothing, then that's a quick way to get rid of all the commas from your data set. So it says 3 replacements were made. Perfect. That's exactly what I wanted. So just kind of a little trick there for you to help you get through some of the data problems that you might be having.
I have a quick question.
I've got a quick answer. Go ahead.
So you said that we have to decide whether we use a negative or a positive root answer. So how do we know from looking at the graph?
So you use a positive root of R squared when your data is sloping upwards, because it has a positive correlation. Notice the slope here of this line is positive. If your data was sloping downwards, and I'm not sure, can you see my cursor very well? If it's sloping downwards, that is, as you move right, the data is decreasing, that's when you'd want to use the negative value for R.
Perfect, thank you.
Thank you. All right, so let's do another one. And there's one just like this in your homework. So this one's example F. Let me see if I can't zoom out a little bit. Now yours is going to be a little different than mine, but what you're going to have to do is actually type in the data. You're going to have to look and say, okay, that's the point, say 8 and 3, and then this is 7 and 3, and 6 and 3, or something like that, and so on. You can use the magnifying glass to increase the size of the data. It's only 10 points that you have to input, but you're going to have to input those. So let's grab this data from example F. Oops, it's not what I want. And I'm hoping that this will paste in better than the last one. I don't know. Give me some feedback out there in either Zoom land or in the class. Is this one working better? Or do I have to change this one too? Is it not working? This is so frustrating. All right. I know it's frustrating for you. It's frustrating for me too. Edit.
Yeah, that didn't work.
Let's try it again. So hit refresh and see if it works better this time. I'll put a version of this in the chat. I hope it's working well there. If it doesn't work, you know, just watch it up here. So this would be example F.
Put it in.
Did it work?
Did you put it in?
Yeah, it did.
I copied mine over to Google Sheets and then copied it from there over to Status, and it worked.
Yeah, I sometimes do that too. I copy it to Google Sheets first and then copy it from there. And it works. I don't know why. It's so annoying. No, I...
Hasn't come up on.
All right, let me... All right.
That one? Didn't come up, right?
It didn't work when
No.
I did it.
Okay.
Copied it in Google Sheets and then
Okay.
copied it again.
Oops, I don't want to go there. All right, if it's not working, then just kind of follow along from up here, please. So we're going to look at this data set kind of in two ways like we did just a minute ago. And for me, I've got the data is in column 3 and column 4. So select those for your X and Y variables respectively. And there we go. There's your output. Let's see. Now we're going to assume that the value of alpha is 0.05. Alpha equals 0.05. Our p-value is 0.22. Nice. 0.022. And we're going to use that in testing H naught. So we're going to test this. Now this means you don't have a significant regression. It means basically you're just going to use the average value of y to make predictions. Here, you've got a significant regression. You can use your regression equation to make predictions. So what's our decision going to be regarding H naught in this particular problem? Are you going to reject H naught or fail to reject H naught? Let's see you guys lighten up the chat with your answers here. All right. All right. Several people there getting in, and I heard a couple of voices here. And the consensus is that our p-value is less than alpha, therefore reject H naught. Yeah, we're going to get rid of H naught. We don't think that that's true. Our p-value is kind of small, so we think we've got a significant regression. You can kind of feel better about that if you actually take a look at the scatter plot. And the scatter plot will show you something kind of interesting. And other than that one point up here, it looks like looks like that little tic-tac-toe worth of dots you open up to get to Google's services, right? But overall, it does kind of look like it's got this pattern. So you could actually use this regression line. By the way, this would be an example, Sonia, I think you were asking just a minute ago. If you were to start out with the coefficient of determination right here, and you wanted to get the correlation coefficient, you'd take the square root, but you'd also take the negative of that square root. And that would be your correlation coefficient, or linear correlation coefficient. So, okay. You can make predictions with this, but the thing that they're going to ask is they're going to go a little farther. what if we got rid of that one value? Because if you look at that one value, that really seems like it's driving this whole regression. So let's get rid of that last value from our regression. Now, when you delete this, hit the backspace key. Do not hit the space key, because the space key can actually enter in a blank character. And sometimes statistics can be kind of fussy about that. So let's reevaluate this. And wow. What do you think about our p-value now? Is our p-value saying reject like it did just a minute ago? No. In fact, it's as far away from reject as it can possibly be. It's a solid 1. It's saying don't even think about rejecting. If you think about rejecting, wake up. If you dream about rejecting, wake up and apologize. Because it's just not anywhere close to rejecting. So, all right. Let's take a look at the scatter plot and try and understand this a little bit more. Look at our regression line that it's fitting there. What's the slope of that regression line? It's a big fat 0. Yeah, there's nothing going on. Knowing the value of x does not help you at all in predicting the value of y. So it makes sense that we don't reject h0. It's just not a significant regression, whereas the other one is. And that makes that 1 point very influential. It's not something that we're going to be worried about in this course, but there are statistical ways to measure how influential a point is. But that's going beyond what we can do here. All right, one last one for this section. And let me see if I can't find it. It's back here in G. No, we already did that one. C. Yeah, here we go. So example C, our last one. And there's a lot going on with this one, and I apologize. But I do want to get to one important point, which is something you're going to see when you do the homework. So it says, for 50 randomly selective speed dates, attractiveness ratings by males of their female partners recorded along with the attractiveness ratings of females of their male date partners. The ratings range from 1 to 10, 50 pair datings. So a lot of background information, but then they give you some stuff like this. They give you X bar, Y bar, R, the p-value, and a regression equation. It says find the best predicted value of y hat for a date in which the attractiveness ratings is a 7. So let me kind of copy down for you some of the relevant information that we need here. This is example C. And let's see here. So example C. We've got y hat equals, and you know what, I forgot to copy some of this down. Let me go here back. Mm, 8.04 minus 0.314x, or I might write it a little bit differently. So let's see. There's also something else I'm going to write down here, and that's the value of y bar. And the value of y bar was 6. Oh, and there's one last thing I should probably write down, and that's the p-value. So I got to go back and find the p-value now. Sorry about that. P-value is 0.052. and our level of alpha is, they don't tell us. Oh, 0.01. Alpha is 0.01. So the first thing you have to do in choosing the model that you're going to use is decide if you're going to reject or fail to reject. What are you going to do about H naught? Well, you've got enough information here to make your decision. And remember, you're making your decision regarding HO is B1 0, or do we believe in HA? B1 is not 0. So are you going to reject or fail to reject? Amber says fail to reject. Let's see. Do I got a couple people in the chat? Yeah. A couple people also agreeing there. Yeah, I agree. Since alpha is greater than P, or alpha is less than P, fail to reject. So that means this is what we think is true. That's what we think is true, meaning we don't believe in the model, which means we shouldn't be using the model. What should we be using instead? Instead, we should be using this. So our model, if you fail to reject H naught, your model is just this. Y hat equals Y bar, or Y hat equals 6. That's your prediction for everything. Your data is no more than just a straight horizontal line. That's it. So that's your predicted value there. And there's at least one like that in the homework, I'm pretty sure. So be on the lookout for it. Because a lot of times people will say, oh, they want to know the predicted value when x equals 7. And that's fine. Usually if you can reject this hypothesis, you put in a 7 here. You multiply negative 0.314 times 7, add 8, and then you get your predicted value. Easy. Couple easy points. But you got to make sure that you're rejecting H naught when you do that. If you don't, then just use the mean, and that's it. Whew. How are we doing there? Good? All right. Let's call it a day on this section. So, any last minute thoughts or questions? All right. Good luck with this stuff.